Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Enrico Belmonte.
Hey, Enrico. Good talking to you again. So what do you got in mind today? I think I cut you off real quick and said, hey, let's record. But you didn't get into any details of what you had in mind.
Yeah, during the week, I always think about what topics I can discuss with Fred. And I think one important topic I really would like to discuss with you is about design for reliability. How can we design better products for reliability, and what are the competencies that reliability engineers should have? I think this is quite interesting topic, and I would like to dive in with you.
Yeah, because we're not mechanical engineers and electrical engineers, software engineers. Some have come from those backgrounds, but that's not our day job now. We're reliability engineers, yet we're asking our teams to design for reliability. And I don't know about you, every now and then I get a blank stare saying, well, what does that mean?
Yeah. No, that's important, because I'm a mechanical engineer, and in Italy, where I attended university, I think there are not so many university offering like reliability engineering curriculum. Basically, I come from mechanical engineering. Then I did I investigated a lot damage mechanisms, and then I moved to reliability engineering field, right? And a lot of people that approach design for reliability, they think reliability is just viable analysis or dealing with data, or they say 90% is that, is dealing with data.
Running tests, running tests and stuff like that.
Running tests, exactly, in the validation, doing tests and see what is going wrong and fix it and this kind of things. But I think design for reliability is much more than that. It's about identifying the leverages for better design, and that for me is really, really powerful.
It is, yeah. Now, what you're talking about is one of the key principles I talk about all the time, and Carl and I wrote about it, is that we identify key decisions, and the program manager says, is it reliable enough to ship, or what's our expected failure rate, stuff like that. And we go off and do testing or evaluations or field data analysis or whatever, and try to inform that decision. But we call those key decisions because they require specific information to be generated to help inform it. But there's so many things that we know in the organization and from our history collectively of engineers from all kinds of backgrounds, that if you design it this way, it'll last a little longer. And if you design it this way, it's not going to work in our environment.
Yeah.
Right? We get this corporate knowledge that if it's harnessed and reinforced and encouraged, it can be a very powerful set of design guidelines that guide your engineers to keep electronics cool and dry, and not load your mechanical systems at their limits, but has some margin in it, and what the safety margin should be and what to consider. If that's not what I have found, if that's not basically written down and encouraged, and just the way we do things here is part of the culture, everybody's going to set their own priorities and say, well, nobody's asking me about the reliability stuff or the DFR stuff, or there's no guidelines here, so I'll just do it the best I can. And you got 3 engineers, you're going to get 3 different results kind of thing.
Yeah. You touch a good point. So the design guidelines. So, for example, talking about also wall thicknesses, for example, wall thickness of a metal sheet. How does reliability change depending on the wall thickness, right? That's a typical design guideline or radius, but it can be much more complicated than that. It could for example, concern the material, or could concern the process. The point is, to me, really powerful to understand what are the leverages I have as reliability engineer. And basically, in 90% of the cases, you can act on stress or strength. There are two different entities. It's not always like that. It might be also, they also might interact. But being clear about what is the stress and what are the parameters affecting the stress, and what is the strength and what are the parameters affecting the strength. That's really, really powerful. And the link between them is the damage mechanism. This is why we always think in terms of damage mechanism.
It's very true. I'm thinking back to when I was teaching design for reliability inside Hewlett Packard. And for the electronics folks, we used a electrolytic capacitor. And there's a coating on a thin foil that then eventually breaks down through mostly voltage strikes or inrush current, stuff like that. But perturbations, usually voltage, causes it to break down. So we would describe that mechanism. And then this is what you can do about it. It's called, in electronics, it's called derating. So it's basically some, recommended amount of margin. And then we found that if you enable your engineers to have the knowledge of that stuff, it really doesn't get implemented, because they still got to go to the next step. Well, how much is enough, and what do I do, and how do I make sure it works? And I'm not tracking the field data to know if this capacitor is working or not. So we just created a table and said, if you have an electrolytic capacitor that's a certain technology, you derate it at 50%. And so that means, instead of, if you have a 5-volt across it, you pick a capacitor that's rated for voltage to 10 volts. And that gives you a 50% derating, or 100% margin, depending on how you look at it. And that got implemented because it was just simple. And it was a simple chapter in our DFR manual that we sent out. And you knew it was successful when you saw the electrical engineers had it on their wall. They had it immediately available. It was a quick table to look up, going, oh yeah, I do that for this technology. But what I find is, whether it's a mechanical engineer in a hardware or electrical engineering guideline or document or lookup table or whatever it is, it allows us as reliability engineers to influence that decision without even having to be there. Right. And that is a huge leverage for us, because we get to make 1,000 decisions that we're not directly involved in. We're enabling them to make good decisions.
And I think the design guideline is the right product to create as a reliability engineer, because is in the design guideline you show the influence or the impact of a parameter on the reliability. So you say, it's like you say, okay, you might want to change the fiber amount, the fiber volume fraction in a material, in a plastic material, but just for a specific extent. Afterwards, the risk is too high, or reliability is too low, right? And coming back to electronics, you talked about before. You talked about how you can dissipate heat, for example. And dissipating heat in electronics is a typical countermeasure on the stress level. You are not touching the component itself. The component remains the same, so you are not changing it. You are changing the stress, lowering the temperature at which it is exposed to. And the reliability engineer, you're saying, hey, I'm not touching the strength, I'm touching the stress. Okay,
that's right.
The damage mechanism is like is aging. for example, and you're touching the stress. If you don't have any leverages or any possibilities to touch this leverage, you might want to say, okay, I take another military grade, for example, component which is resisting
higher temperatures.
at
It's rated for
higher
higher
temperature.
temperatures. Yeah.
Exactly. And this is strength. This is strength leverage,
Yeah. Yeah, and it's a good way to think of it. Years and years ago, a colleague that was in a failure analysis lab said, a really good way to do design for reliability is take every single component and list all of the failure mechanisms. I said, oh, okay, that's going to take a year. For even a simple product, that'll take a while. And then list out all of the strengths and stresses. So do a stress strength curve for every single mechanism you got. And okay, this sounds impossible, he says, but the out is use the knowledge of your engineering team to say, all right, what are the weak points? What are the areas of least margin? What are the areas that we have the most uncertainty? What are the areas? It's like an FMEA almost. And then you end up with 10 or 12 things that you got, all right, we need to understand this better and figure out what the right margin is or what the right offset is or whatever. We don't need to intimately, consider and model and design every single component on the system, because we've been using, resistors, surface mount resistors for 20 years now in our team, and we don't have issues related to that. So if we keep doing what we're doing and don't mess it up, we're in good shape. And we don't have time to study a 100 ohm resistor before we launch this thing, and all the other stuff that we know is going to be a problem or could be a problem. But the design guide, I think, is only one facet of design for reliability, right? I think there's something else to it. I think, from what I understand, what you do on a day-to-day basis, it's that training, it's the culture part, it's the why we care about reliability. This is answering the question across the organization that, right, we did this product this way, we used these tools, we did these techniques, we had this changes to our design practice. And look at this, 6 months in, it's got half the failure rate of a similar product after 6 months. That accounts for so much money.
But you said training is really important. But if you train, if you empower people using this kind of reasoning when it comes to reliability, and instead of saying, let's fix the problem, let's find the root cause, let's fix the problems overall. You say, okay, what is damage mechanism? What is the stress? What is the strength? What are the available options we have for mitigating the failure rate, for example. That's if everybody's thinking these terms, it is much faster, and efficient to work.
Yeah. And I think, and what I have found is that some people say, well, what's in it for me? They'll ask that question in various ways. It's like, well, if I do this, the procurement people are going to be mad at me because I have to use more expensive materials or parts in places. And it takes an extra step. It takes time to go through and make sure I select the right components and do the other steps. And he says, this is the baseline. It's a simple thing, probably the simplest thing we can do for a good design for reliability program. And the training and why we do it is a piece of that. The awareness, this is how we do it. This is why it's important. Here's how much money it saves. But there's other people that are like, I already don't have enough time. And I say, well, why don't you have enough time? Because we get to near the end of the program and it goes through test and all this stuff fails. And then we're running around trying to get it all fixed. I says, this is exactly why we say the design guidelines and thinking through or the FMEAs and block diagrams and focusing on failure mechanisms helps, because you can fix it early on and it doesn't happen later. And that is generally really hard to prove that it was valuable when it didn't happen. Right?
Yeah, that's always
that's right.
Yeah.
So if there's no problems, I think one of the competencies of a good reliability engineer is to say, all right, we did the training, I double checked, we saw it in the reviews. They're doing these different kinds of FMEAs and thinking through failure mechanism, design guide application. And hey, look, we're in the final design review and you guys are all panicking. All the verification testing went really well.
Yeah.
And it just say, and that's because you designed in the reliability. It doesn't just it doesn't just happen by chance. Give them
No,
credit
no.
for it, right? We got to
Yeah.
be able to claim that value, even though it's often not seen. And that's a tricky thing to do, to sell something that's not there.
Yeah, that's exactly what's happening in the mature organization, where reliability engineers are doing properly their job and they are recognized knowledge for their contribution without
Mm-hmm.
without being heroes, solving problem last day before or even after the start of production.
Yeah.
But yeah, you said proper way. So if we start training and empowering people to use the tool, not because the tool that have to be used, in order to be a good reliability engineer, but in order to say sort out the concepts, and talking all the same languages and using the same logic. Yeah,
Mm-hmm.
it
Mm-hmm.
helps a lot in the design preview. Therefore, I'm saying when I talked about design for reliability, I attended a lot of reviews where people were in an unstructured way trying to solve a problem, because
Mm-hmm.
it's faster. But basically it's not faster,
No, usually not. Yeah.
Yeah. So yeah, and basically, if you don't know the damage mechanism, you cannot identify the proper stress and strain. Then you optimize somehow. You optimize somehow the product, but probably in the wrong direction.
Yeah.
And then you don't know why you have done it, and it's like technical depths that are
Yeah.
increasing, over
Yeah,
time.
yeah. No, it's frustrating when you get that where they say the worst is when they come to you and it's after they've tried 3 different rounds of fixes for it, and they says we just can't get a handle on fixing it. And right, well, what's the problem?
Yeah.
What exactly are you trying to solve? Right, that's a symptom. You can patch that symptom all day long and never fix it. What's the actual mechanism? What is exactly going on? And
Yeah.
sometimes that's difficult to find. And so people tend to shy away from that. But I put that in the training too. This is how you do failure analysis. This is why it's so important. And here's the range of tools we have available to do it really well. And yeah, it takes another day or two in most cases to sort out what's going on here, but then you have an answer. Then you have something you can go
Yeah.
fix.
And then it comes, you can teach about a statistic, for example, no? Because if you say, hey, I have identified the damage mechanism, I know the stress, I know the strength, then you can say, hey, the stress is not constant, is variable. The strength is not
Mm,
constant, is variable. So when you have a worst combination between high stress and low strength, then you have probably failed.
yeah,
The part is going to fail, right?
yeah,
And that is, I think, is much more intuitive than starting from just saying, okay, this is the viable distribution. Yeah.
yeah. Oh, here's the PDF and the CDF and the reliability
Mm.
function and the what's the other one? I'm drawing a blank.
Yeah. Yeah.
There's 7 distributions with Weibull or functions, I should say. But the idea is that, yeah, that's the most boring way to teach statistics by far. But if you can teach it where it's all right, we know the environment it is in, and here's the stresses that we expect to see on this product. Here's the distribution of them. And then you now figure out, well, this is what the distribution is, and here's how you use it. Um, but I'm going to go back to the DFR one more time. It's failure mechanism is a big deal in it, but I think there's also a part where there's always trade-offs, right? Even
Mhm.
if I know all the failure mechanisms, I'm still not going to have time to solve them all. I just won't have budget and time to do that. There's a lot more things that can go wrong and we can understand than we have time to design out of the
Yeah.
product. So things like FMEA and HALT allow us to identify areas that that are things we really should go fix because and we can do them early in the program when it doesn't cost as much. And we don't, I mean, understanding the failure mechanism in each of those cases is different than understanding all the failure mechanism because both those tools tend to give you a shorter list of priorities. I'm thinking of other tools is
Yeah, DRBFM, for example, is quite a good tool for doing that, because with DRBFM you are really reproducing the failure mechanism. You are forced to draw, to draw the damage mechanism, together with other people to discuss what's can go wrong at much deeper level than the FMEA.
Yeah.
That's generally I use the DRBFM when it as a counter, as a countermeasure when we identify a big risk in FMEA. For example, if you need to change material, if you need to change a process or the design, the DRBFM is a great tool because you are doing through the impact analysis, then risk finding and resolving. You are doing, you're going really into detail, describing the damage mechanism and identifying what are the countermeasure for robust design. These are all tools. I think there are some more than what we have just mentioned. You mentioned FMEA, you mentioned so the stress strength interference methods, the DRBFM.
There's HALT, but there's also
the
tools.
HALT, yeah.
But there's tools built into our design tools also. I know the mechanical tools these days almost all have FMEA, or not FMEA, finite element analysis capability. And there's folks that have computational fluid dynamics tools so they can monitor heat flows.
Yeah, simulation,
and simulation tools. And I think a lot of those help us understand at first the design trade-offs. How can I get this function to work given the constraints I have? And I almost always want to connect with those people as a reliability engineer saying, all right, what happens when that filter gets clogged with, dander and cat hair and stuff like that? What happens if the other parts of our environment we know are going to happen? As that material ages, will it have the same resilience that it does now? And the material science, no, it won't, right? Well, how much different will it be? And they add that to the model, and we can then do the trade-off analysis to say, will this still work? I don't see it as often as I like in organizations, yet the use of simulation is a wonderful tool before you make prototypes to really analyze not only the initial design trade-offs, but include, and it really relies on that our interest in failure mechanisms and our interest in why we want to create a reliable product. Then it is encouragement and reinforcement of using the design tools and the simulation tools we have available to good effect. So there's a wide range of tools out there on the design side strictly, or on the quality. One we didn't mention at all, and I want to mention it before we wrap it up, is do you use capability indices, CPKs, as information into your design team?
No, generally I don't use it, CPK, for reliability, for function analysis. So we were used to do that, for tolerances analysis and functional analysis.
So I think it's a reliability thing, right? If the designer is assuming that this could be cut and bent to this tolerance, and it's not, and it affects the performance of the product, then we can calculate the impact of that. If it's 1 in a million problem, then don't worry about it. If it's 1 in 10 units are going to be out of spec, which I worked with one organization, the designer needed really, really tight designs, but we didn't have the technology to create components to those specs. And it's like, then it was a management decision. What risk are we going to take? And they added redundancy to the system to compensate for that problem. But the idea is that I find CPKs back into those tolerancing discussions is critical to help us identify where the critical dimensions are and
Yeah.
what's capable.
No, I
And
think in these terms, so we used to work with worst case sample, that are
mm-hmm.
coming from CPK analysis. That's definitely they can be integrated in simulation, for example.
Oh yeah, and using worst case is a great solution if you can create a design that works under that. Because there's so many cases I've run into where we have so many worst cases. There's no way this thing could ever be assembled
Yeah, and
or
that's of
used.
course the combination of worst case is a big problem for reliability engineers.
It is, yeah.
So, but I mean, this is where distribution comes into play,
Oh yeah,
because if you have the CPK, you have a distribution that you can compare against the strength distribution. But
that's right.
generally, it's not so easy to take the CPK, so the functional distribution, connect it to the reliability distribution, stress distribution, and then compare against the strength distribution.
Well, yeah, that's a whole other podcast then, because it's using
Yeah,
Monte Carlo techniques. You can, I've seen it work really, really well. But that
with
might be
Monte Carlo, you
another.
said.
Yeah, using Monte Carlo,
Yeah,
you got a lot of
yeah,
information there. You
yeah.
can combine those things, and it's a bit of work to set it out. But yeah, it's there's a range of tools out there. And I think you're right in your earlier comment. There's more than we're going to mention in our time here.
Yeah, I have just two tools just as scenes for future discussion. One is AI.
Mm-hmm.
So how about conversating with AI, asking for what can be potential consequences of failure, what is damage mechanism related to this component, what might be the risk we are going to find designing this way. And I think so, like copilot, AI based copilot could help a lot in the design teams,
Yeah, no, that sounds like
basically
a good topic.
incorporating a lot of, yeah. And the other point I would like to mention is on the material level and on the process level. But on material level, I was used to um, investigate what is the best recipe for material in terms of polymer and compounds, because as
Mm-hmm,
soon
mm-hmm.
as you improve one property, you are
Almost always messing up something else. Yeah, you
yeah,
might
you
improve
have
tensile
some
strength, but
gaps.
it's the strength
Yeah.
tensile strength might be great with this improvement, but it deteriorates quickly in UV light and just falls apart.
And that is really important to know the damage mechanism, because if
Yeah.
you know the damage mechanism, say, okay, impact strength is really important, so let's optimize it, even if I'm saying just the Young's modulus is decreasing because it's not important. Yeah.
Mm-hmm.
And this kind of things, yeah, design for reliability is really important. Is the awareness of what are the direction I need to take when optimizing design or material or process. I cannot take all possible direction because this will be over design. But knowing what are the potential damage mechanisms, I can identify the directions to be followed for improving the design.
Yeah.
That I think is really powerful tool for reliability engineer. And that should be the fundamental knowledge and competencies of reliability engineers. Then, of course, it should be also combined with data analysis. But for example, the use of the software tools, right? This should be just at the end, just to support you in the in the analysis.
Yeah. No, I agree. And I didn't mention it earlier, is when I was at Hewlett Packard before my time, they did a study across all of the divisions in the corporation, and they were looking for best practices for reliability performance specifically and we had internal failure rate data and warranty type data and stuff like that. So we kind of knew the divisions that did really well and the ones that didn't. And so Dick Moss went off and surveyed them basically through interviews and conversations to find what did they do that set them apart. And the better company, the better resulting organizations really implemented the DFR tools well. So derating and stress strength and, and all those kinds of things. FMEA was in the top of that. And the organizations that didn't do any of that stuff or didn't even know what it was, really did suffer in their relative warranty costs, compared
Okay.
to similar products. So there was very clear evidence that these DFR tools work. So they put a lot of money and time, effort to build and adopt and teach and encourage and use these DFR tools across the corporation. And it helped a lot. But
Mm-hmm.
it has to be reinforced. It's not just that the reliability engineer knows these tools. It has to be across the team. All the management teams, all the engineering teams have to understand that this is how we design a product. It has to include derating. It has to include these design guideline best practices. It's those kinds of things kind of clean all the stuff that we should design out without having to overthink it too much. Just design them
Yeah.
out and then focus on the critical few to really focus on those and solve them and get them work out of the design. So
Yeah, I think an expert is fundamental, but it should not. The organization should not create like silos. No.
that's right. You don't just send you the design here, Enrico. You got 2 weeks. Finish the design so it's reliable now.
Yeah,
That's not going to happen.
that's definitely not the right way. I think the simultaneous engineering team, as I said multiple times, is the best way to do that because
Yeah.
you have a team for a product or for a component. They work together, and they as you said, they are not everybody is expert in his or her own field, but they can understand and they are aware about the contribution that the other people can bring. And that's, I think, is the best recipe.
Yeah. No, it works. It's DFR is more than just a set of tools. You got to implement them. And I think that's the core competency of reliability engineers, is getting your organization to that level. But if you're listening to this and going, oh, you forgot to mention this, or this is how we do it and stuff like that, or what's working for you or not working for you, let us know. Head over to accendoreliability.com/go/SOR, and you can find a couple of ways to get in touch with us. Enrico and I and the other hosts are available through LinkedIn and our About pages. So there's plenty of ways for you to get in touch with us. And as you've heard me say it, I don't know, 1,000 times now, maybe more, we really do want you to join the conversation. We really do want to hear from you. And if you send us a question, we'll try to get you an answer pretty quickly. And once we talk about it, it's almost always an update to what our initial response is, and we'll get back in touch with you to let you know what else we could recommend. But it really works best when you participate with us. So we look forward to that. All right.
Thank you, Fred.
All right. Thank you, Enrico. Good topic. Glad you brought it up. And we'll talk again soon, I'm sure.
Yeah. Bye.
Bye-bye. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.